search where is this mux gate, right? This keyword, module name alone, mux gate. Yeah, it's here. Select this and give OK. The moment you give OK, two more windows open up. Let me see what are they. They are called as object window and one more process window. Process window, of course, it has nothing to do now. And one more simulation default, their corresponding signal. So these two windows open up. From the project, it will move to simulation. Means it has been changing from the mode of HDL code writing to simulation mode. So once you get this object, now you select the list of objects that need to be listed out in the output. By pressing Control button, you can select one by one, or you can also use Shift button. After selecting the first one, you can give the last one. All the intermediate signals will be selected in a single click. So you are supposed to select those signals which you want to display that in the waveform window. Remember, all the intermediate nets, you need not have it. Now after selecting, right click, add to waveform selected signal. Once you give like this, you get something like a waveform window. You can unlock from the deck so that it becomes little more bigger in size. Yeah, this is the one. Now I need to test whether it is behaving as a mux. Originally speaking, I can write another one code and give all possible combination of A and B and S and see whether your output is coming up. That's called as a test bench. Time being, since we have not seen the test bench, I am not going to that. I am just leaving as it is and deliberately forcing. This is a mechanism by which I deliberately force a value to this. Look at here, selecting all this, but don't select output. You cannot force a value to the output. You can force values only to clock and the inputs. So select only the inputs, right click, go to force. Now I can simply give, the signal is A. Let me give 0 for that. It's a single bit. B signal. Let me give 1. Next. Select. Let me give 0. That's all. After giving this value, of course, you can't see this now. You can see after you run that. Now you could say I am keeping it here. Now look at this. A is 0. ST 0 means strong 0. B is 1. Select is 0. It will pass the value of A. So A value is 0. You are getting 0. Now let me make A value to 1. Go here. Use the force. Make it as 1. Now again resimulate. Now you could see this A value has been moved from 0 to 1. And you could also see now Y has been moved to 1. Now let me make B to be 0. Let me force B to be 0 and select line to be 1. Let me do like this. Select line to be 1. If I make select line to be 1, then it should select the value of B. Now let me simulate this. Yes. See here, select line is 1. So this value, B value, should be in my output. I am getting my output. So you can even zoom this, all those things, you can just do that. The output again can be exported as, go here, export as an image. You can save it as a bitmap file also, BMP file, which could be used for all the documentation purpose. That's all. Up to this point, if you have any doubt, you can stop me and If you are okay, then you can start coding it. Either the same 2:1 mux, and in addition, I will give you a simple half adder. I believe you know the circuit for an half adder. A half adder has a sum and a carry, right? A sum is A XOR B, carry is A dot B. Is this clear? Now please start writing the coding. If you have any doubt, you can just ask me now. I could feel a dead silence here. Yes. Any doubt?
Okay, sir. No doubt, sir.
Yeah. I just want, I'm giving some 5-10 minutes, 5 minutes. Please start coding it. So, language you can learn only by practicing. So, for half adder, I'm just giving the circuit. You can just build. Sum is, in fact, you can write using data flow style also. We will shortly see the data flow style. But before that, let's go ahead with the same structural modeling. A XOR B carry A dot B, which mean one XOR gate, one AND gate. So two signal A, B is here. This is my sum. This is my carry. This is much more simpler than the earlier one. Quick. So let's take a break of 5 minutes. Before that, uh, if possible, please let me know where you stuck up, because you have all the programs here and there. You can always download and work it out. But the thing is, I'm just trying to at the maximum try to expose you how to write a code and get the confidence of writing the code. The real way to start coding is blindly start writing the coding. Definitely you will make mistake. Don't care about that. uh, Later on you can master it. Yes, we will take a break of 5 minutes. Okay, welcome back. So I believe you could write that code in the gate level. Now let's move on with data flow style. Do you all hear me?
Yes, yes, we can hear.
Yeah. So for data flow style, one important thing which you need to keep in mind is the operators. I'll just quickly give a review of all the operators. So thereby it becomes easy for you to keep in mind. Now look at here. The main syntax or the constructs which is used here is assign. We have already said, and the variable on my left hand side should be declared as wire, or by default it should be a wire. Now only thing is this right hand side has variables and the operators. Now only thing we need to know what are the operators and how to use that operators. You have enormous number of operators. I am just quickly concising it for you to understand under this category. Arithmetic operator, bitwise operator, reduction operator, logical operator, relational operator, shift operator, selection operator, concatenation, and replication. These are very high, and in fact, you can practice this couple of times in writing the code. Then alone you become still more, familiar. So like these are very trivial. For add, you need to use plus, subtract minus, multiplication star. You should not resemble this with. That's the point which I would like to say. A star B is not same as A ampersand B. This is multiplication, whereas this is bitwise AND. Those things you should be very, very conscious. And this division operation is okay with simulation, but it is not synthesizable code. If you are using division operator, that will not be supported while you go for synthesis. Power, you need to use double star. Modulo operation, this is a modulo operation, and all the other things are same. I'm just giving, moving on towards that. And the bitwise operation, as I said, bitwise, this is an unary operator. Unary operator means not. Yes, tilt of yes means not of yes. These are binary operators. So A ampersand B means and, bitwise and. Let's consider A equal to 101, B equal to 010. So A ampersand B is and operation of this 000, everything will be 0. So this is OR, XOR, XNOR. In fact, the tilt can be given either before or after, like this. You can, these are called as the bitwise operator. Then subsequently following this, in a single operand, if you give this, it is used as a reduction operator. Means subsequent bit following bit will be performed with and or things like that, and the final output will be a single bit. Since it takes too much of time, I'm just skipping it out. There is a difference between A and B and A double ampersand B. What does this mean? It is a bitwise and. This mean logical operator. If this is true and this is true, if it is Monday, if it is 5 o'clock, then the classes for Verilog will start. So this is a logical operator. Similarly, you can have in the equal to itself, we have 3 equal. See, look at here. In fact, not 3, even more than that. One time equal, double time equal, triple time equal, equal with bar. This many operator you will be using. But remember, all are being used with the used in different place with different context. This is assignment operator. Y is being assigned with this value or expression. This is equating operator or validating equality. A equal to B. If you add like this, A is not equal to B then. If 3 times equals symbol is being given, they take into consideration of X and Z also, whereas here you take into consideration of zeros and 1 for equating whether A equal to B. That is considering X and Z case, you have case equality. This is non-blocking assignment. This is blocking assignment. This is non-blocking assignment. We will see shortly what is the difference. That's all. So you see here, this sort of comparison should be made while you study. Then alone it becomes easy for you what operator, where to be used, how to be used. Right. Okay. I'm just skipping out quickly. Greater, smaller, greater than, less than, all this shift operation is something like this. Shifting a bit towards your right by single bit. This is for your left bit. Okay. And one more is given here. This one. In fact, you have this sort of this statement in C also. That is conditional expression, question mark, true operation, false operation. Right? Now let me use this statement for 2:1 mux. Say I will write like this. Assign all the other statements, everything remains the same. I am just going to this this one, 2:1 mux, except this portion. I am writing like this. Assign, because assign is the operator which has been used in data flow style. Assign y equal to, see here, y I haven't written anything like reg, so by default it is a wire. Y equal to condition yes, question mark, if yes is true, B value, else A value. That's all. A single line, instead of this whole code, I can just replace that by a single line to write this statement. Can you follow this one? The same mux with a single assign statement, y equal to yes, select line, question mark. This is a condition verification. You can give an even expression also. If this expression turn out to be true, then this is the true expression. This is a false expression. That's what it has been shown over here. So condition expression, question mark, true, colon, false. So you can use this for coming up with the 2:1 mux. The same code I could write in the data flow style in another way too, because already I know the equation for y equal to a s bar plus b s. This is the equation. When do we go for data flow style? When we know very well the Boolean expression that relate these two. Now let me write this. Assign y equal to a. Now this is AND operation, bitwise AND. Tilt of s bar. So this whole thing can be given inside this. Then b ampersand. Yes, that's all. So a single line with operators and the variables. So instead of writing this many number of line, I can replace this line with this line also in the data flow style. Is this clear to you? The same thing for half adder, full adder also. If I want to write this, I will write assign sum. Only thing, sum and carry should be a wire. Sum equal to A XOR B. Assign carry equal to A ampersand B. That's all. That's as simple as this. Now the same thing has been done. Let me show you, because for the want of time I am not writing the code one by one. I'm going to enter mux. Let me add everything so that it becomes yeah. I think it is added in this project. Then it is not getting reflected. It takes a little bit of time. Let me stop this simulation. Add to project, existing file. Go here. I'm just including some of the files. What is this? I think it has already added, but only thing, it takes some time or it is not reflecting. One more update. Let me give update. Oh, that's what. It has already updated everything. I mean, included everything. Now, I am just giving compile for all these files. Compile all. There is some error with some files. Okay, let me check it out. Right. Now let us see, someone should find out what is the error in this. Oh, always I didn't teach you. That's, let it be as it is. Yeah, someone can find out what is this error. Yeah. Can someone say what is the error in this one?
Input B is not declared.
Yes, yes, yes. That's it. That's it. Right. I have made a mistake there. Okay, that has been ruled out. And if else we have not seen that, maybe after looking into that, we may come across that. Time being, let it be as it is. Okay, now the point which I would like to show you is, yeah, go to this case. Now see here, a simple case statement, sorry, no, case statement, design statement, which is in data flow style, has been shown to you. Has been shown to you. Uh, if you the same procedure, go here. Now you need to go to simulate and see mux case, and then give appropriate input. You will get the same thing. Similarly, the same mux has been done in gate level. All this if else equation again you can show it in this way. Full adder, look at here. So full adder expression is a xor b xor c. Carry is a dot b plus b dot c plus c dot a, right? So c is here c in. So typically I have used two assign statement to do that. Very simple, you can make a full adder. Now I believe you understood how to make or how to write a code for gate level, and the next one is data flow style. Now let's go with something on um, behavioral level. Everything remains the same. Here the main thing is I'm going to use two important constructs, that is always. This always have multiple information. I'll just quickly say what are those. So always is a construct being used. It can be used for both combinational circuit as well as sequential circuit. If it is a combinational circuit, it is being used as always at, say, same for this same mux x1 comma x2 comma s. This becomes the sensitivity list. This is called a sensitivity list. Sensitivity list. What do you mean by this? Whenever this value changes, immediately this always loop will get executed. The beauty of the always loop, there are two such loops. In fact, one is always loop, the other one is initial loop. I'm just sorry. I'm just listing out the difference between these two. Always get executed n number of time. Or what I mean to say is, whenever this any of this sensitivity list value changes, immediately it start executing this. Whereas in the initial, it doesn't have any sensitivity list, but it will get executed only once. That's the difference. Always is being used in the design. Initial is being used in the test bench. Always get synthesizable. It cannot be synthesized. Which one? Initial. All always block. If my design has 4 always block, or always block or all initial block execute in parallel. This is also in parallel. But inside an always block, it may get executed in parallel or sequential. It depends upon the operator which you are going to use. Inside a sequential block, it is in sequence. When inside an initial block, it is being executed in sequential. That's all. So an always block, mostly it is used for all designs. You can also use it in test bench also, but majorly it is being used in the design. So this is called sensitivity list. If it is just a signal, then you can use it as a signal in combinational circuit. In case if you are planning to use this always in something like sequential block, then it becomes like this. Always, whenever I say sequential, it is with respect to clock. So you will be using the keyword pass edge or neck edge. It may be with the clock or reset or clear, anything. Passage of the clock, neck edge of the clock. What does this mean is, whenever my clock move from 0 to 1, this is called passage. So I am syncing all this operation inside this always block with respect to passage of the clock. You get executed, I mean, these set of codes get executed only if the passage of the clock happens, right? Or you can give it as an edge of the clock in case if you want to sync all your operation. Well, my clock goes from 1 to 0, it is negate. You can give passage of the reset. Yes, if the reset moves from 0 to 1, you want to do certain operation, you do the like this. You can keep on doing it. So whenever you have passage neckage, immediately you can conclude these are sequential circuits, because they are the circuit which works with edge triggered mechanism, right? Okay. Whereas if it is with some variables, then this always statement is used for combo logic. That's the point which we mentioned here. And one more thing, as we said, all the variables on my left hand side inside an always block should be a reg. Variables should be reg. Inside an always block, I can use three important constructs. One, if, else, even you can go with nested if else also. Say something like this. If reset, by default, if I don't mention anything, it means that reset equal to 1. If reset equal to 1, y equal to 1 tick binary 0, or y is being assigned with 0, else y equal to d. If I mention like this, then you could see it's a simple if else statements. You can also go for nesting of if else statement. That also possible, as you do with C. This is one way to do that. This is one construct inside and always. Otherwise, you can use something like a case. Say something like this. Case. Select. Let me consider inside and always. I am just giving the core point of the code. Case is again a statement. Case x, yes. Let me assume that the case is a select is 2:1 mux selection. So if s equal to 1 tick binary 0 colon y equal to a. If s equal to 1 tick binary 1 colon y equal to b. End case. That's all. Or since if s has a possibility of having x and z, then you add one more line, default. Any other apart from 0 and 1, you have y equal to z. That's it. So what it means to say is, a case statement which has a variable here, you can have n number of possibilities. Say if s is 2-bit, then I can have 0, 0, 0, 1, 1, 0, 1, 1. Say I'm having a control line like this for a ALU, right? So 0, 0 control line, it should perform addition. 0, 1 control line, it should perform subtraction. 1, 0 control line, it should perform a shifting operation. 1, 1 control line, it should perform multiplication or bitwise AND. So like this. So this control line, it could be a control line, with 2 bit. So 2 tick binary 00, 2 tick binary. So output y equal to a ampersand b. That will be my output. Or a plus b, it is an addition operation. If it is 0 1 control line, y equal to a minus b. I am just using arithmetic operators. 1 0, y will be equal to a multiplication of b. Then y equal to, this is 1 1, right? 1 1 control line, y equal to a power of b, like this. Only thing, if you have the case here, you need to end up with the end case. Again, remember, end and case doesn't have any space between them. So you need to have end case. And one more thing, inside an always an initial block, if there is more than one statement, you need to have begin and end. Why do we need this begin and end? You know very well, whenever I keep anything within this begin and end, all these instructions are being executed in a sequential fashion. So that facilitate a sequential. That's all. So we have seen what is an always statement. When can I use always for combinational circuit? When can I use always for sequential circuit? And inside and always, how do I use if and else? Inside that, how can I use case? One more, um, yeah, with respect to operator. Say, look at here. Always, I'm just doing like this. Always, sorry. At a comma b comma c, begin, y is assigned with a dot b, x is assigned with b star c, right? Yes, end. See, this is not same as, in case if I am using, instead of this equal to operator, if I am using this operator, then the value will be different. The reason is, look at here, using this operator and this operator, this is called blocking operator. This is called non-blocking operator. What do that mean is, if you are having multiple statement like this, though within the begin and the end, if I am using equal to symbol, it will get executed one after the other. It will first execute this. In case if you are using y here, and I would have used here, let's assume that I have used here. So this value, updated value, will be used for computing this expression and get this value. If I am using non-blocking statement, this is for blocking statement. Blocking means it blocks the execution of the remaining line until unless the previous line get executed. This is called as non-blocking. Non-blocking means you are at the same time instant, all the values on my left hand side will get computed and simply deposited on this. It's a parallel operation. This is parallel, this is serial operation or sequential operation. That's all. That's the way this operator makes a difference. So either you can have a blocking or a non-blocking. That's all. So that's it. We have completed even behavioral level modeling. So we can again go ahead and see what is the mistake or the error that has been listed out in that using if-else statement. Get back to the code. So we have made mux using if-else statement. Now, can you just let me unlock it so that it becomes easy for you to see. Yeah, tell me what is the mistake here.
The output should be at the first, sir. The inputs are available under first. I mean in the function mux if else.
Output should be reg.
Correct. 1 minute. So anyway, so while you say something, then it is easy for me to correct. Okay, look at here. When I say module, I was clearly mentioning that this port list, you can keep it in any order.
Okay.
No way it create a problem. The reason is I am explicitly defining the here which is your input and output. But when it come to primitive, you don't go there and say which is your input and output. In the primitive, the first one should be the output. In the gate level, whenever you write the code, the first one should be the output, subsequently following the input. Even the input order can change. That won't create any problem. But the problem here is, look at this, always at a comma b comma s begin. If s equal to 1, I said y being assigned with b, else y being assigned with a, begin and end, everything is fine. But only problem here, y, I didn't write this as reg. That's the problem.
Yes.
In fact, you can also cross verify the error. Um, yes, let me remove this reg and then see what is the error it is giving. Go here, compile selected. So this is my error. Sometime the error will propagate. So if you correct one error, subsequently all the other things get ruled out by itself. Line number 7, it says illegal reference to net to y. Yes. So by default, net or wire both means the same here. And illegal reference to net y in line number 9 also. 9 also. So both the places you have this at. So I am just making this at reg will solve this issue. Control S and again going back, compile selected. Now it got sorted out. So again, you can go with the same procedure, like go to simulate and start invoking this, right? Go to simulate mux if else. Expand this work. Go to M. You will be having mux if else. Means only after compiling you could get this module name inside this work folder. Otherwise, you won't get. See, you have here, right? Then you can open it and you can cross verify. I think we will stop that there itself. Now, fine. We have seen 3 styles of coding. Of course, the same thing you can see with respect to case. I think there is one more with case. Yes. See, this is with case. Look at here. I have used the same thing. Only thing in the case of this particular variety, I have used case yes. So one tick binary 0, y equal to y is being assigned with a and y is being assigned with b. Default I have said this is a very simple statement. So you can assign that with all this possible. So we have seen how to use if else, how to use case inside an always block. That too, now for all this, this always statement is used for combo logic. I didn't go with sequential logic. Sequential logic, I mean anything which is operating with the passage or neckage of the clock, then it be considered as this one. Okay, let's stop there. Now, one more thing, I just come back with this. Maybe we can wind up after you finish this one. And tomorrow we will be seeing purely sequential circuit and FSM. Now look at here. I would like to make a 4-bit ripple carry adder. I believe you know what is a ripple carry adder. Means 4 times full adder. So first of all, let's see what is half adder. Half adder, 2-bit adders. Like you can add 1 with 0, 0 with 1, things like that. Full adder, you are being permitted to add 3 single bit. 1 plus 0 plus 1, something like this. 3 bit at a time. Right? This is full adder. Like this, I am making 4-bit adder, like A equal to 1011, B equal to 0010, something like this. Now this is B0, B1, B2, B3. This is A0, A1, A2, A3. I am supposed to add this. So what I am doing, I am calling 4 times full adder. So this is full adder 0, full adder 1, full adder 2, full adder 3. Why full adder? Because look at here. For this I can give, this is how you add, right? This is A, for B you put over here 0, 0, 1, 0. So you are adding A0 with B0. So 1, like this. So I am giving A0, B0. But sometimes you may have an initial carry, C in. This I am giving it here, C in. Now you have 3 bits, 3 bits to be added. So definitely you need full adder, not a half adder will do this work. In case if C in is not there, definitely you can do it with half adder. At the end you will be having sum S0. Carry also you will be having, but this carry has been passed on to the next stage. That is, let me keep it as C0. And here A1, B1, and this will give you sum 1, carry 1. This will be passed on to the next stage. That's the reason it is called as ripple. You could see the carry get ripple from one stage to the next stage. So here it is sum S2, carry is being forwarded C2, and this is okay. This is A2, B2, A3, B3. Here you will have some 3 bit and the final C out. That's all. I call this as a ripple carry adder because the carry has been rippled from one stage to the other stage via this critical path. Or what I mean to say is, this circuit, if it want to get completed, or if this full adder need to be in operation, before that these two adders should have completed its computation and it would have passed the result. Only for this adder, only if it get the carry from the previous stage, it can start its computation. Otherwise it can't, right? So the carry become a bottleneck, right? It's a very modular adder. Means, what do you mean by modular? See, I can write a code for only this full adder, call this n number of time, even 16-bit adder, even it is 64-bit of adder. You can simply copy one line, call that for n number of time. Only thing you need to change the corresponding input variable and output variable. Otherwise, the functionality remains the same. Because already you have written a code for a full adder. How does a full adder look like? Right? Okay. So this is a problem for ripple carry adder. Otherwise, it is a modular adder where your structure keeps on get repeating. The output is typically like this, like n plus n give n plus 1 bit as our output. Now, to do this, or to write a code for this, what we do is, you write a code for full adder once, call that 4 times for a ripple carry adder. That's what I am going to do. Let's straight away go to the code. First, let me see the full adder code. So look at here. This code is written in data flow style. because we use operators. I believe you could follow this one. A, B, C in as your input, sum and carry are your output. I have assigned the sum equation and carry equation. So you have written this full adder code. Now let me go to ripple carry adder 4-bit. Now come here. This is the point. Now the top module is ripple carry adder. Only thing, I am not going to write anything new. I am going to call the earlier written code for full adder 4 times. One more point. Look at here. This is my module. This is my end module. I can call some other module inside my module, right? Say like full adder, which you have written a code for the full adder. I can call some other module by its module name n number of time, but I cannot go and define a module inside a module. Do you understand the difference between these two? I can call a module name inside a module name n number of time. Example is, look at here. If you look at this code, this is my module name, module full adder. This module is RCA4B with this the code end. I have called this full adder 4 times inside my ripple carry adder 4-bit. But what I mean to say, you cannot take this whole code and keep it inside this module. So you cannot define a module inside a module, but you can call a module by its module name inside a module. This process of calling a module by its module name inside a module is called module instantiation. Means I am calling n number of time inside a main module. That's it. That's what we have done here. Right. Now look at here. So I have called the, since I have used ripple carry adder 4 times, I am calling this full adder 4 times. Now you see here, this is my instant name, A1, A2, A3, A4, you can give anything. Here port mapping of input and output. What do I mean is, this is the full adder code. I have followed this order. The first one is sum, second one is carry, then A, B, C. While you call this inside your module, you follow the same order. Say like S0 will be given as sum, C0 will be given as carry, this input will be given as A0, this B will be given as B0, because in the first full adder you could see A0, B0 has been given as an input, right? I am just port mapping by order. This is called port mapping by order. So it will, when once it calls the full adder, it will directly come to this code. Of course, it need not be in the same file. You can keep it separately also. I can even delete this here, because already you have a submodule full adder in this project, but it need to be within that project. That's more important. So you could see this has been, so what it will do, it will take all this value of A0, B0, Cin, pass it on to this program, compute the value of sum and carry, and substitute in this here sum 0 and carry 0. Similarly, second time when you call adder, it will feed this value as an input, compute this and feed this as an output. Like this, it immediately takes the input by the order or port map by order. This A1 will be mapped with this A1. In case if I am giving the B value here, then wrongly it would have marked. So while I instantiate a module, you need to port map by order, or otherwise you can port map by name. Means what do I mean by that? Look at here. port map by order is says sum, okay, adder, sum, carry, A, comma, B. If I'm calling this for n number of time, like module, adder, this order should be same here too. The first one should be the sum. You should not go and keep this as a carry in your in the module description. So whatever order you kept here should be followed in the instantiation also. So it will take the third one as A, fourth one as B, second one as carry, the first one as sum. This is port map by order. In case if you don't want to have such confusion, what you can do is port map by name. So instead, let me keep I keep X, Y, Z, and W. Then you can port map something like this: adder dot S is being mapped with the X, dot C is being mapped with Y, dot A is being mapped with Z, dot B is being mapped with W. This is called port mapping by name. I am explicitly saying this signal is equivalent to this signal. So these are the port mapping while you go for module instantiation. So here I have very few number of signals, so there won't be any confusion in the order. So I have used port map by order. So always the best option is you use dot port mapping by name, like sum 0 has been connected with sum, dot co has been connected with carry, like this. That's all. So you could see this is called as port module instantiation and port order or port connection by order or port connection by name. Is this clear? In fact, you can check this. Possibly we will check the answer for this, and with that we can wind up. So go here, RCB4, simulate, start simulation, go to R RCB, yes. So okay. So now my input signals are A, B, Cn, sum and carry. So right click and send it to selected signal. Somewhere it went. Okay. So now let me give values for A, B. It's a 4-bit. A, B, and Cn. 4 set. Let me give 1010 for A. B is 0010. Now let me give this to be 1, Cn to be 1. That's all. Now let me start simulating it. Uh, Now the sum and carry has not been given a value. Let's see what's the mistake in that. Sum carry, okay. Can someone find out what is the problem in this? So this is 10. 10 is 12. 12 plus 1, 13. C count is, sorry. Let me change the value. Something wrong here? See out. So let's take the first case, A0, B0, C in, and yeah. C in, C not. Can someone find this error? Any error finding?
Sir, does it matter if we give extra space?
No, that doesn't matter. That doesn't matter. Only thing I believe the same variables are being used.
While giving the input, can we make C in as 0 first, and or can we make C in as 1, A and B as 0, so that we can check whether 1 is coming or not? We can give the initial input for the carry as 0.
No, that's coming. That we have checked. That's we have checked. A X or B, X or C, that's fine. Okay, ladder you have instantiated, right? But why does it carry? It seems to be right only, but somewhere some mistake is there in the logic. It shouldn't matter, but still.
Actually, it had showed me some error in a port list if I gave extra space. That's why I told.
Where?
That you deleted, no? That port list, the full ladder program that you
Okay.
had written.
Yes.
So if you give extra space, it will not show the output properly in the port list while defining the port list.
You mean to say here something? Input A, comma B, comma right. So
Sir,
what
there is a dot sum. Output
output? Yeah,
sum.
yeah. This is where there is a problem.
Yes, sir. No, it's okay. But it's taking as a dot.
No, it is taking this a dot. Okay. I will just remove this portion and let's make this as A comma B comma Cn comma sum comma carry. Let's do this. Now let me remove this portion also. Carry is it comma B comma. Is it dot or something else? Yeah. Right. Now let me see. Compile this one and this one. Okay. To compilation has been done successfully. Let's see for full adder. Start simulation. Full adder. Sorry. Full adder. Okay. Yes, I have too many programs which has been sometime I was thinking add to waveform selected signal. Let me force something. Yeah, you have. Let me delete this. A, B, C in force it 1, 0, 1. Let me do some simulation. Yeah. So A, B, 0, 1. So sum is 0, carry is 1. Let me make this as 1 and see whether that works fine. Yeah. Now 3 ones. Yeah, that's working fine. So as far as full adder is concerned, it's working fine. Now let's go back to the project. Go to simulate ripple carry adder RCA. Four bit. Let's start from here and let me Okay. Add it to waveform. Selected signal. Yeah, let me give input for these three. Force 1010. Oh, next, so let me give 0010. Let me give 1. Let's see. There is something else wrong. Some mistake with respect to the port mapping. Port mapping or with respect to signal instantiation. And this is should I make this shouldn't mind it, but still let me see. It's time up. I think there is something like dot. It is. That's not the one, I think. Okay, so let's do one thing. I'll just try to debug the code, and the people, you can also go through that and see if there is anything wrong. Then we will get back tomorrow. Maybe let it be an exercise for you too. So already we have crossed almost 3 hours. So let's stop here and find out what is the problem tomorrow, and we will try to solve this. Okay. So tomorrow we will be concentrating more on sequential based circuit, like starting from flip flop latches, and then use that for a counter. That way we can do it. So thanks for joining your and for your patience. We will meet tomorrow.
Thank you, sir.
Thank you. Thank you so much.
Thank you.
Thank you.
At the same time